Hello, my name is Harper Mangine, and this is my Physics 2211 Lab 1 report about constant velocity. So the purpose of this lab was to observe an object moving at a constant velocity, and it was used to compare an observed reality to a computational estimate of motion using Newton's second law, and it's also gave me practice coding in WebVPython glowscript. Key assumptions in background: f net of x is 0 due to constant velocity, and there's no resistance, either air or friction, and then that the object, the little car, travels in a continuous straight line in the positive x hat direction. The important principles used in this lab are Newton's first law, that an object at motion or at rest stays in this state unless acted on by an outside force, and in this case it's in motion. Newton's second law, which is the momentum principle, and that the acceleration of the body is directly proportional to the net force acting on the body and inversely proportional to the mass, which can be described as F net equals delta P over delta T, where derivatives are not applicable, and P is mv, delta P equals m delta V, where P is momentum, m is mass, velocity, V is velocity, and T is time. I also use the position update formula, where R is my final and initial position, and the velocity update formula, where V is my final and initial velocity. And for the sake of this lab, those two are equal to each other because it was moving at a constant velocity, and that is also equal to the average velocity. So the procedure was I had to start by defining the variables in the system being the car, the surroundings is everything else, and the variables are the initial position, final position, average velocity, gravity, and the net force. I then had to record a video of a small weighted car rolling across a track about 1 meter in length at a constant velocity. I then had to import it into Tracker and track the car's position from center mass frame by frame for about 1.5 seconds. And then create a computational estimation model of the car's motion by editing the starter glowscript code, and then create a graph of the actual position of the car versus the computational estimate of the car over time, and compare both sets of data and draw conclusions. So my initial conditions, I chose my time to be 0.133 seconds and my position to be 0.129 meters. And the note for this is that in my tracker at 0 seconds, the starting position is negative and extremely small. It's a 10 to the -4 number, and starting at a solid distance and time, it made the computations much more consistent and a lot easier. My net force of x is 0 because it's a constant velocity, and my only net force in the y direction is negative mass times gravity, which is just a gravitational constant. My initial velocity and my velocity was 0.824 meters per second, and my position update vector was 0.028 meters. So the results preview, the computational motion prediction was a linear line in the positive x hat direction, starting at 0.129 meters and moving up by 0.028. The actual motion is linear in the positive x hat direction. However, the graph deviates from the computational line towards the end due to the car slowing down from friction and air. However, these forces were deemed negligible for this lab. So this is my tracker. And this is my glowscript computational estimate. I've seen that it is basically just a straight line, and the velocity is at y equals 0.824. The comparison, the computational estimate is straight, and the observed kind of deviates towards the end, and that is due to the forces acting upon the car that were deemed negligible in the sense of this lab. And the tracker is estimated over a 1.5 second interval, and the jump at the beginning is just from where I chose to start it at 0.133 seconds instead of 0 seconds. Possible sources for error, other forces, like I said, friction, air force, however, those were deemed negligible, and the rounding errors, tracker and glowscript are based off of estimated values that I chose, so there is a risk for human error because I'm the one making these choices. For the lab questions, the first what if question, if it were to flip axes, the slope of the graph would just be negative. And then the what does it mean question. In this lab specifically, it's difficult to determine all the forces acting on the car, as many of the significant ones were deemed negligible, such as friction and air resistance. And the force of gravity is constant, so it is assumed the car is only moving in the positive x hat direction. Thank you.